Hi guys, good morning and welcome to this episode of AM Friday. I'm Nick Martin.
And I'm Daniel Young. Let's get to it.
So we have one Markforged update this week. So you may have seen that we've released a new material, Onyx FR. And so this is a version of our Onyx material that you probably know and love, but it's V0 rated, which means if you were to ignite it, within 10 seconds, it's self-extinguishing. So it's a fire retardant version of our Onyx.
Yeah, well, I think one of the most common pieces of feedback we receive on Onyx is it's a really cool material, but it's not, the one thing that it lacks is that if you set it on fire, it kind of behaves like a normal plastic. So this is very similar to that Onyx and just resist that. So we have a cool video to show you it just at the very beginning before we get started of just an actual test of Onyx, our existing material versus Onyx FR, the V0 rated one.
Yep. So to illustrate that, we'll show you this video we got. So on the left is our regular Onyx material, and on the right is our new Onyx FR. And you'll see as the Onyx ignites, not only does it propagate the flame, but it actually begins to drip it.
Yeah, and so one thing with the difference between, like, say, a V2 rating, which is what we say our Onyx is generally close to, and a V0 rating is that the dripping of flammable components is something that happens. So Onyx is actually more flame resistant than, like, some plastics. It doesn't actively, like, catch on fire and spread flame super seriously, but it does definitely drip. And so FR is a completely different thing where it's actively self-extinguishing. So the moment you take the flame away, it stops.
Great.
Cool. So yeah, and the other notes, it has the same heat deflection temperature because that has to do with more the heat of the working environment. This is specifically flame resistant. And so where we see this being specifically helpful is in the aerospace area where everything has to be V0 to be on flight hardware, the automotive area, and other kinds of places near like that.
Yep. So now that we've gone through some updates, today we're going to be talking about 3D printing manufacturing tooling, and more specifically, how metal 3D printing can fit into stamping die tool production. And excuse me. So we'll talk about a couple different metal forming applications with Markforged printers. And like I said, we're gonna focus on how you can do it with metal 3D printed parts. But first, you may have heard of one of our customers, Centerline Engineered Solutions. They have one of our composite 3D printers, and what they do is they do some sheet metal forming.
Yeah, so we're going to spend most of this time talking about a metal application because for most stamping, forming type applications, one of the key things is having high surface hardness and the ability to hold an edge, both of which are just not things that our composite printers can do. However, for some forming operations, especially for ones that are what's called pre-lanced, so which means basically they're cuts already made in the metal, the composite material with fiber reinforcement can actually withstand stuff. So I'm not sure, I'm looking at the stream here. It looks like we can, you can see like the actual slots in this material. So this is the actual blank that Centerline, this job shop in South Carolina, used. It's pre-lanced and it's lanced on a plasma cutter. So that plasma cutter cut little lines, relief lines into the metal. And then after that, this composite stamping die, which you can see here that Nick is showing off, with these four kind of little bumps here and then corresponding depressions here, are used to actually form a piece of 14 gauge sheet steel. So you can do it in some places on composites, but for the rest of this, we're just going to talk about metal.
Yeah, and so I actually have a picture here of this in action. So this goes on a press brake, and as Daniel mentioned, it forms into these divots here, these four divots.
Yeah, so we're going to share if we get the chance. Cool.
So there it is on the press brake, and then
yes, this is a many-ton Trump press brake. That's the final part. It goes through a couple of bending operations after this, but it's a cool story behind this part. They were able to actually, this part was a low-volume sheet metal part, which is not for forming, just generally doesn't agree. Those are not terms that work together. Mm-hmm. So the tooling that they originally kind of had spec'd to machine for this was too expensive for them to actually give a meaningful quote on the part. And by being able to print it, the cost went down to the point where they could actually make this part. So it wasn't as much a cost savings as much of as they were now able to fabricate a part they could not fabricate otherwise. So really cool application there.
Yep. So that's a quick overview of one of our customers using composites for some cool sheet metal tooling.
But yeah, so we're gonna dive into metal now. Yeah.
Yep. And so stamping dies are another animal where you're typically using tool steels to pierce, blank, and bend metal. And so when you have these operations that are a lot more abrasive, where you're actually cutting metal with an edge and forming metal on the order of hundreds of thousands of times, we need a lot more robust tools.
Yeah, and sheet metal's everywhere. So everything from like your car door, like something to a giant piece of sheet steel, to like the coins in a paper wallet, to the frames of this table. Basically, like sheet metal is like rolled sheet metal is like one of the fundamental tools of fabrication, just universally. And so being able to kind of enter this field, at least in some areas, is something that's very exciting to us. And part of it is because we're launching more tool steels as the year goes on. So right now we have H13, which is a hot work steel. It's maybe less optimized for this, but we're launching A2 in the pretty near future, and D2 down the road as well, which are more familiar as cold work tool steels that you could use for this application.
Yep, certainly. And so if you're unfamiliar with the stamping die tool production process, it's similar to a lot of other manufacturing tooling, where you're going to start with a design in CAD, whether you're 3D printing it or creating it with a traditional way on a mill. And so you're going to design it in CAD, but with stamping, one really important step is after you've designed the part, designed the tool, you put that geometry into simulation, which simulates the actual stamping process. So for example, if you're going to have a piercing and blanking die, which is what this one is, what we'll talk about, this one is for washers. You want to simulate that process and do some FEA analysis of what's actually happening with the sheet metal, because especially when you're drawing sheet metal, you're straining the metal and plastically deforming it.
Yep.
And so there's some spring back that can happen that you want to be able to predict, so you can get as accurate as you can on those parts.
Yep. So if you want to kind of harken back to like a typical stress strain graph, you probably know that as Nick says, all of sheet metal fabrication is due to plastic deformation. Even with plastic deformations, things usually rebound elastically, or what's called spring back in the sheet metal term. So being able to simulate not only how the forces are going to interact, but how the little motion of the part is going to, how the part is going to move or change shape after the forming process really informs the shape of the form.
And then conversely, if you have strictly a piercing process or a blanking process, you want to make sure that your edge is actually cutting through the part, and instead of deforming the part, you're just cutting through it.
Yep, and so tolerances are really key there as well.
Yeah, exactly. And so there's a bunch of simulation tools out there that engineers use, such as Stampak, where you are predicting how it's going to act, and that way you can tweak your design before you go into final tooling, which is the actual really expensive process of making a tool.
Yeah, so with the soft jaw, you're basically holding a part that you know the shape of. With stamping, you're stamping a part into a certain geometry, so with the intention that it's going to spring back into your goal geometry. So having simulation there is really critical, and it's been a huge step forward in the sheet metal process, especially with making more complexly shaped parts. So if you think about how like car doors have gotten, or car parts have gotten a lot more intricate, a lot of that is due to the fact that stamping and simulation has taken a large step forward.
Yep. And so, as I mentioned, the iteration on the design happens in this process when you're simulating. And then afterwards, if you're going to machine this tool, which is how basically every single stamping die tool is made right now, you're going to process it in CAM. So that's where you're going to be choosing your tool paths and choosing the tools you're going to be using to machine this piece of tool steel. Which, as you probably know if you're involved in machining at all, this is A2, machining A2 is not an easy process. So aluminum is a metal that's machined a lot, and it's one of the easiest metals to machine. But once you start getting into these tool steels that are a lot harder and tougher to machine, you see a lot more tool wear, which is expensive, and you need to do some more careful planning in CAM with your tool selection and your tool path selection.
Yeah, it's harder, it wears out the tools more. As we said, this is like, our A2 is, A2 is typically in the 60 HRC range, where even like a 17.4 for reference is like 36 to 40 depending on heat treatment. So it's a whole different animal, and you generally will machine and then you heat treat, but even pre-heat treated, this material is just hard. It'll wear down tools, and you need to be really careful with your tool passes, and as a result, the fabrication costs for an A2 part or even H13 part are just much higher than your aluminum or even like standard stainless steel parts.
Yeah. And so the CAM process is something that's carefully planned, and then after that process, the part is machined, and then after the shape is machined, with a stamping die tool, you're always going to harden it because it's going to be in this really high wear environment, and so you harden it, which is just a heat treatment process. And afterwards, you want to test your die, and so typically through all those steps that I just went through, you hope to arrive at a fully functional production die at the end, because this is a pretty expensive process. So you test the die, make sure that you're getting the parts that you want, and then afterwards, hopefully there's no design rework. If there is, then you have to redesign the die, and then you can go into production. And so that's pretty much how the process goes right now. And so what we're going to talk about is how metal 3D printing can be interjected into that process to reduce the number of times you have to rework the production tooling, and increase the speed at which you can get from your design to your production tool.
Yeah, I think we talk pretty commonly about how design rework is a painful process, like kind of across the board, and that is true for like for almost every part. For something like a stamp, where you kind of all these pre-processes laid in, and then you have the difficult machining process, specifically on some stamps that are larger, having to rework a tool or having to kind of iterate can be catastrophic. Like where some things you kind of expect to iterate on these stamping tools, you really want to get it as correct as possible the first time. That's got to be the goal, just because of the cost of the process.
Yep, and so as we've talked about a couple times, the advantages of printing things in metal is that you get to largely skip that machining process. You may have to do a finishing pass on the mill, depending on what sort of tolerances you're looking for and what sort of surface finish you're looking for, but you don't have to take away all of that material off of a solid block of tool steel, which number one, saves your machining bandwidth, and number two, saves all of your tools.
Yeah, and it gets more and more advantageous the more you kind of uniquely shaped your stamping die is, because a stamping die that's a block you might be able to kind of stick it pretty close to a normal shape of stock, but something that's kind of uniquely shaped with more passes, that's where 3D printing, again, like everything else, gets a lot cheaper relative to the
and so we've talked a lot. We actually have an entire AM Friday about picking parts that are good for metal 3D printing and picking parts that might be better for other traditional manufacturing methods. So we won't dive too deep into that, but the general, as Daniel said, is the more complex geometries, and then once you get into this realm of tool steels, when you can print it and the part works effectively, it can be a lot less expensive and time consuming to print it rather than machine it.
Yep.
And so, in terms of the parts that you can actually use in a stamping die process that are 3D printed, we've done a lot of thinking of this over the past week. And there's some parts that, admittedly, you should not metal 3D print in the metal stamping die process. Most of the parts actually should be made the way that they have been made for a long time. But there are a couple specific areas that have not really been iterated on, that we've been making stamping die components the same way for pretty much 100 years, that could use a revamp with metal 3D printing that can really complement it.
Yeah, and so you notice the things we're going to talk about kind of all occupy that same space, where they're geometrically complex. They're usually not too large, and they're things that kind of can really that you can produce with 3D printing faster than you can maybe turn in a typical cycle.
Yeah, and so these parts include the actual working faces of smaller stamping dies. So this is an example of one, as I mentioned. This is for a washer. It's a blanking and piercing die. So parts that are doing blanking and piercing, like this one, or bending, that aren't incredibly large, as you know, because the envelope that you can actually print a metal part in is not massive. And in addition to those working faces, heel blocks are another thing that are interesting to explore with metal 3D printing. And if you're unfamiliar with stamping dies, heel blocks are essentially so when you have your stamping die, you have the actual part that's pressing the sheet metal, and so that's what I say when I mean working face. But that is fixed to precision ground guide pins that are making sure that you stamp the exact same geometry every single time. And so when you stamp sheet metal, there's a lot of forces that are happening that can actually deflect that tool as it's stamping, because it's under an incredible amount of pressure. And so when those forces are experienced, if those forces are transferred to the guide pins, those guide pins can actually deflect and cause your process to become inaccurate after just a few cycles. Yeah. And so to avoid this, it's essentially you use what's called heel blocks, which are these blocks that are precision machined, welded to the shoe of the stamping die, and then they interface with each other. They have wear plates on them that interface with each other that basically equal out those forces that are in different directions, because you want to keep your force unidirectional when you're using a stamping die.
Yeah, stamping is kind of a unique system, because in typical systems you kind of use a pin as something that would take shear force. Like shear pins are very common. There's something where they can serve both kind of an alignment and a load bearing process. Because of like the massive forces it takes to actually bend and shear metal, you really don't want these alignment pins, which are machined to like 1/10,000th of an inch, so incredibly tight precision. You don't want them loaded too heavily because they become unusable, and your stamping system becomes poorly maintained, and things start to go out of whack. So the heel blocks are there to take the force so that your alignment features can focus on basically being alignment features. And so, as Nick says, they're in multi-materials, and they're often uniquely shaped because a heel block is not something that's a general piece of hardware. It's something that's unique to each type of to each individual stamp. Yeah. So these things where you have one that's a harder one and one that's, you could say, a more sacrificial one, but really just is intended to deflect more, they both, depending on the materials you print with, could be printed. And so where you can get these unique geometries and kind of optimize around this is a really interesting place.
Yeah, exactly. And depending on the directions of the forces that are experienced during that specific stamping process will determine the geometry of those heel blocks. And as Daniel mentioned, these are usually made in multiple materials. So aluminum bronze is a common material, and tool steel, some sort of tool steel. And so the reason it's two different materials is because two of the same type of metal have a higher coefficient of friction when rubbing against each other than two different types of metal. And so that's why two different types of metal are made. We don't print in aluminum bronze, but we do print in tool steels. And so as we start releasing our tool steels to our customers, we see this as a possible application space.
Yeah, and I wanted to pause real quick. So feel free to ask questions. We'll try to get to them as we go. We could take a quick break for questions now. So we had a couple people ask just the basics of printing. So what are the design precautions? How are heating processes done in them? How to validate the simulated part by which it's fabricated. So I guess design precautions, we have a couple design guides on our website that are super useful. The design precautions of 3D printing are our metal 3D printing process, which I'm kind of assuming you're talking about here, pretty similar to our composite ones because it's an extrusion-based process. So the minimum feature sizes and kind of on how to talk about like orienting parts and designing parts, they have a good interface with the build plate. Those are all kind of similar. In terms of heating processes, for our metal printer, after we sinter the parts, which is kind of part of the process, you can use just any standard furnace with any standard heat treatment process to kind of treat the actual parts. And then simulation, so simulation is kind of a bit of a trickier thing, but something we're actively working on here.
Yeah, and so it looks like next question. Durability and max carrying load, it can carry for A2 tools compared to machined ones, max printed size. So we haven't officially released our A2 tool steel material yet, so I can't point you to the material sheet just yet. But I can say if you look at our material sheets for the metals we have released, like 17.4 pH stainless steel and H13 tool steel, you'll see that we are achieving loads that are pretty close to wrought steel.
Yeah.
And so we're talking about 95, 96% of the strength.
Yep. And then, so someone else asked a tolerancing question, which I'll get to right now. So it says, what kind of tolerance can you get to on the diameter of a punch after sintering before final grind? So in terms of tolerancing on our parts, it's something where we're still kind of defining the proper spec, and the thing we always say is it's geometry dependent, because it really depends on basically what type of stuff you're printing. For a simpler part like this part in my hand here, which is just basically a series of cylinders that are decreased in diameter, it's more accurate than, say, a really complex part. But that kind of takes us back to kind of what we're talking about, especially the working faces, which we'll get into a little bit more. And when we're thinking about working faces, like in the long term, machining working faces for final parts is probably still a better application for most things than printing them. Just for the final die, it works better. It'll probably last longer, and it's probably a better process. The places we see the working faces side fitting in are kind of twofold. So one is like a lower volume part. So we're machining a complex working face where if the cost is higher, basically makes the overall, if you distribute that machining cost to the cost per part of the actual sheet metal, pushes that cost too high. Something that if you're looking for vaguely, like slightly lower precision or a slightly cheaper process, that really works. And then the other space is kind of prototyping working faces. So as we said previously, the process is very long and very reliant on simulation. If you can print your working faces, depending on the size, you can see if they're producing parts that make sense before actually making your final part. And that's an extra step of validation on top of the simulation, so that you kind of you decrease your risk of having to rework a stamping tool.
Yeah, and we'll dive a little deeper into that in a couple minutes. But in terms of giving you an answer for tolerance, as Daniel said, we don't have an exact number, but a part like this, we are typically within several thous.
Yeah.
So those are the two working faces and heel blocks are two good application spaces we see. And then the third one is stripper pads. And so these you can actually make out of with our composite printers. And stripper pads, if you're not familiar, are basically parts that help remove the sheet metal that may get stuck to the tool during the stamping process. So like we said, you're yielding the sheet metal when you're stamping it, and so that metal can actually stretch across the tool and get stuck to it. And so stripper pads are something that basically scrape that off of the tool to get your final part. And so making these out of onyx is something that we've seen that is positive.
Like a similar type of part would be an ejector pin on a mold. The issue with an ejector pin, generally in this kind of high force process, is if you're working with sheet metal, the ejector pin might actually mar your material or form your material a little bit. So the stripper pad is a way to remove your metal part without actually affecting the shape of it or risking something like that. So it's usually spring loaded, and it sits on it's mounted to the top plate. And then after your bending process, it helps pull off from the bottom plate.
Yeah. So those are the 3 application spaces that we see that could be positive for 3D printing within the stamping die tooling space. But as I mentioned, most of the parts should not be 3D printed. So for example, die plates and shoes, which are basically the giant tool steel mounting precision ground pieces of hardware that are used in stamping processes that really take a lot of the brunt of the force and have to be really precision flat, are something that are better to be machined, especially since they're really large pieces. And then guide pins, as we mentioned, Daniel said, have to be precision ground and are really regular geometry, which makes it so they're simpler to make using traditional manufacturing. Springs are something that you can easily buy off the shelf. Bushings, for example, are another example of something you can buy off the shelf. So a lot of the hardware, the really large, regularly shaped stuff, the really high precision stuff, and then the stuff that you can buy off the shelf are really good options for keeping it the traditional way.
Yeah, and also for what it's worth, at this point, just capability-wise in metal 3D printing, there are very few metal processes that can make giant, precise parts. Ours is definitely not one of them. The max part size on ours is not that large relative to stamping. So for larger stamps, you're going to still have to machine parts. So when we're talking about places that forming surfaces can fit in, it's definitely in the smaller envelopes.
Yep. So Daniel touched on this a second ago. What situations is it good to actually 3D print some stamping die components? And so one that Daniel mentioned is prototype dies. So the ability to verify the design with an actual tool before you go into creating your production tool is valuable for a couple different reasons. One, Daniel already mentioned, which is having the ability to make sure your parts are exactly how they want to be before you invest in the tool. So if you have to do some design iteration, you can do that without having invested tens of thousands of dollars or thousands of dollars into a stamping die tool. The other advantage is that, let's say you make your prototype die and you start running it, and you find that the parts are exactly how you want them, you can run that die while your production tool is being created. So you actually get increased or decreased downtime. You're actually making parts while you're waiting for your tool to be created, which could take on the order of weeks or months when we're talking about these precision stamping dies.
Yep.
And so those are the 2 main advantages of 3D printing a prototyping die. A second one is for short runs. So stamping is something that has largely been reserved to mass production because, number one, it's really expensive to make stamping dies typically, especially the larger ones. And 2, it's a process that, as I'll mention in a second, has been really iterated on to be perfect for mass production.
Yep.
And so short runs, if you want to make sheet metal but you don't want to make 300,000 parts or 1 million parts of one sheet metal part, then you're kind of out of luck because that tooling cost can't be spread over 1 million different parts. The cost of the tooling is only divided among 1,000 parts if you only want to make 1,000 parts. So you end up getting a part cost that is pretty high. And so you either, one, have to give up on the quality of your die, or number 2, just find a different way to fabricate it. And so if you can bring the cost of that tooling down for a short run, it opens up the opportunity to stamp parts that are really efficient to stamp but may have been prohibitively expensive before.
or generally you see on lower run parts, just sheet metal is less common.
Yeah.
Like especially like sheet metal, the complex forming sheet metal is pretty rare on low run parts, and so the reason is that the cost is prohibitive. So now you see the advantages that sheet metal brings, which is like the ability to make super unique mounting surfaces, like surface geometries that kind of violate what a typical machining rules would be, and all these things that are distinct design advantages. You can kind of bring them down to lo-fi tools. And that being said, like for something that's lower run, you don't need to use a super hyper optimized like stamping cell or a press brake cell that you might see in a production area. You could use a much simpler thing. So these things here, this composite one in particular, was run on just a Trump press brake that's by no means built for like large scale, like many part production. It's more of it's a machine shop style tool, and so that you can bring that kind of level of intricacy down the funnel towards more towards like I guess lower budget shops or lower budget areas.
Yeah, exactly. And so the next thing I'll talk about, I have a picture of to show you guys. But one development that has happened in stamping dies and stamping die tooling recently is progressive stamping dies. And so what if a progressive stamping die, this is an example, this is just the picture off of the Wikipedia page, you can check it out, but progressive stamping dies essentially take components or sheet metal parts that take multiple stamping operations. So maybe you have a bending operation, a piercing operation, and then a blanking operation to take the part out. And it puts all of those tools on a single tool. So that tool, this one has, it looks like 6 steps. So you stamp all 6 steps at once, and then the sheet is on a conveyor that moves down at a specified speed. So as the stamp pushes each time, it's doing 6 operations at once. And so this allows you to massively increase the throughput of the parts that you're making. And we see, you can look it up, you can see progressive stamping dies that have 10 or 20 different tools on one die. And so this is, as you can imagine, extremely expensive to make because you've basically taken a tool and added 6 times as many operations to it. And so this is something that's very expensive and not something that you would necessarily print the entire tool for. You wouldn't, that Toyota stamping die tool, you wouldn't just take that giant block and print it on your printer.
Normally you take that and you take a giant block of tool steel and you take it into your $100 million machining center and precisely mill out those things. So and it's also worth noting why you would do a progressive stamping tool like that. So if you look at that the result of that Toyota emblem there was like a part that is mostly blanks and then a few thin areas. So if you tried to punch out every part of that at once, it would seriously deform that internal structure. So if you look at how they do it, they progressively stamp out areas that are not near each other so that it's not that the stamping doesn't actually mar the final part. And so that allows you to create more complex stuff through steps. And so as Nick says, a whole big block might not make sense, but you can isolate different parts of that block.
Yeah, and so the future of making these progressive tools is that you can make modular tools that can be 3D printed that are smaller pieces, and by placing those modular tools together, you can create multiple progressive die tools that get put together into one block. Because what you're doing, as I mentioned, is with a progressive die, you're making 6 or 10 tools at once. And so being able to have those custom tools 3D printed can be a lot less of an expensive process. And just for a ballpark number, progressive stamping dies can cost $30,000 or even more. So we're talking tens of thousands of dollars that if you can cut down the amount of time it's spending on the machine, amount of time it's spending being processed in CAM, that's a huge money-saving operation for mass production.
Yeah, so and we said like a lot of the innovations in stamping come at the absolute top end of the actual process. So like progressive stamping comes from like car manufacturers, right, or something that and so one thing that the metal 3D printing can do kind of across the board in stamping is make some of these more advanced capabilities perhaps available to low-fi areas, or make them cheaper and more accessible. And so that we view as a big opportunity. And I think generally when we're talking about this, it's a place that still needs to be proven out largely. I think like figuring out like the intricacies of how stamping works in terms of 3D printed parts and things that we need to simulate better, and how we can make more accurate parts. These are all kind of things that have to be answered. But we do think that in terms of where the Metal-X works, this is a really interesting application space.
Yep, certainly. And so I also have a picture here of, so we mentioned this die here. This was printed out of A2 tool steel on our printers, and in this picture you see this is a washer that was stamped by this die. And so, as we mentioned before, the 3D printing tools we see as being useful for these smaller tools that aren't You're not going to be 3D printing tools, at least right now, for giant doors of cars or aluminum bodies or casings of cars. You're going to be seeing it for these smaller parts where it's more useful.
Yep, absolutely. And so in this case, that stamped an aluminum washer, it did a pretty good job of it, and we did it in a very lo-fi way. But the core kind of requirements are there, and so we think it's a really exciting space.
Yeah. Certainly. So if you guys, we had a shorter amount of content today, so if you guys have more questions, we can take those live now, and we'll give you a few seconds to put questions in that chat window.
Yep, and also they can be stamping related, they can be Metal X related, they can be composite related as well. If you have just general Markforged questions, we're happy to answer them.
It looks like we had a question that we missed before. Is an automobile metal part like a hub, knuckle, and gears to be 3D printed? So this is a good question. We get this one a lot as well, where a part like a knuckle of a car is something that's very complex, and you think it would probably be good for a 3D printing process. But that's a part that's being mass produced, and typically right now it's a casting process they're using to make that part, maybe post-machined for the critical dimensions. And so the traditional ways of making that part now are probably the best way to make it, especially with these large steering knuckles that you may be talking about. But a way that 3D printing can be input into that process is during that production process of that part, the work holding for those complex parts, if you're post-machining it or if you're moving it around on your factory floor, can be printed out of these wear-resistant tool steels or onyx, depending on what the part is. So inputting 3D printing into that manufacturing process, while maybe you're not making an end-use part for those larger pieces, you can be using this supportive hardware that's non-revenue generating that may be sucking money out on the back end.
Yeah, I think you could potentially, depending on the size of like a hub or a knuckle, you could print it probably on like a consumer car. Might be a bit too big. Those are typically cast and machined. But yeah, and then someone asked gears as well. We've actually seen some gears printed. It really depends. I think that they're possible. You can print them. It's not always economical. So if you think about it, gears are typically a COTS or a consumer off-the-shelf type of thing. So you can usually find gears. There are some. If you kind of get away from that, the process to make gears gets a lot more expensive. You can wire EDM them. You can machine them, I think that's really not the happiest way to do it. Or you can print them. So we've seen some printed gears work. They're usually things that are kind of uniquely shaped, or like they're weirdly sized, or they're small gears or something in that area. It's possible. We don't generally recommend you print hardware though.
Yep. Another question. Let's see. Can you change the design or direction of the infill structure for a tool steel section? So this is a good question as well. One thing, and a request that we get a lot is for post-machining being able to, so our metal parts are printed with an infill, with a lattice infill, as we've mentioned in previous episodes. And so a lot of times the option to print more roofs and floors and walls to get those really thick sections for post-machining is something that people want, and is something that we're working on. And so right now, changing the infill in metal parts is not something that we allow yet. But it's something, more customization as we make sure that parts will always succeed with those settings is something that is definitely coming.
Yeah, and I think so some things we'll see as thicker walls are one thing, and solid parts to a certain size as well. I think the things that are coming. Someone asked, what hardness do you get on this punch after heat treatment? We haven't officially launched A2 yet, so I don't think we're quoting, this is printed in our A2. Obviously, we print stuff long before we launch it. I don't think we've quoted a final hardness data. When we launch A2, which should be in the pretty near future, my guess, I'm sure we'll give that. Just for reference, wrought A2, if you heat treat it, can get up to anywhere from like 62 to 65 HRC. And if you kind of compare for H13's sake, I think we're generally like a little bit below what the wrought spec is for hardness. H13, which is another tool suite we've launched, is hardenable, and you can go look at our data sheet and talk about how the hardness, if we've hardened it versus like kind of a typical wrought hardened process. But I don't know the max number right now, but we'll get to it at some point. Someone asked if they saw a fire retardant version of Onyx recently, or any other new materials on the composites and metal side. Well, we just talked about FR at the beginning. Onyx FR is what it's called. It's V0 rated, super cool. And then in terms of metals, as you said, A2 is the material that you're typically making stamping dies out of now. It's something that's coming down the pipe. There's a number of other ones as well that are kind of in progress or in development.
Yep. What is the density of the punch after sinter? So another question we get a lot, and so there's a two-part answer to this question. As I mentioned, our metal parts are printed with an internal structure in them that's like you've seen in other printed parts, it's like a triangular infill. And so if we talk density of the actual part as a whole, including open spaces, that's something it's not a fully dense part. But if we're talking density of the actual parts containing metal in the metal part, then we see densities around 96%, 95%.
Depending on the material, it's like 94.5 to 97, I think.
Yeah, depending on the material.
Yeah.
So, hopefully that answers your question.
Yeah, and so as you said, it's surface. It's in the current iteration of the Metal X, it's kind of dependent on your ratio of your surfaces to the volume. So a big box would have a lower relative density than something like this that has a lot of that's relatively thin and has a lot of walls. But the overall, when we're the place we're trying to put metal, it's vast majority metal. Cool. Are there any other questions? It looks like I don't think we have any other questions at this point. If we'll give one more minute to talk about that. In terms of future AM Fridays, I think we're going to do one in a couple weeks. We're still figuring out the exact way to do it, but we are kind of like we're going to continue kind of talking about the Metal X and how it fits into the application spaces.
All right, so one last question before we sign off. Can you print a section as big as the print bed will print and sinter outside? Have you done this? So I'm assuming the question is sintering using like a MIM furnace that's not our furnace. So two answers to this question. Printing a section as big as the print bed and sintering it, even if you were to sinter in a large MIM furnace, the furnaces like that you may see, the giant ones, we showed it on the show last week, are not meant for giant parts. They're meant for a ton of tiny parts. And so the problem of sintering big parts is not unique to our process. The MIM process has been tackling that problem for decades as well. And so I would answer that question with the Sinter 2 is coming out soon. That's going to be able to fit a lot larger geometries. But typically when you have a larger sintering furnace, it's best for sintering more small parts than sintering giant parts, because large parts are difficult to sinter and always have been.
Yeah, I think generally it's like high volume parts. Sometimes you can print a long part and you can expect to sinter it all right generally.
Yeah.
When you get those large blocky parts, just because of the geometry of how parts shrink, that can start to be a little bit kind of difficult to actually deal
Certainly
with.
something we're working on and getting better at with printing larger parts.
It's one thing where you kind of have, the larger your data set gets, the more you can kind of tune how you're designing parts and how we're printing parts. Someone asked if we've done CIP on a printed part. I'm actually not familiar with that acronym. If you're talking about the closest thing I can think of is HIP, hot isostatic pressing. So on this part, we did not HIP it. I don't know. It could be cold isostatic pressing. If you could like maybe list that, maybe we can get a better answer. In terms of hot isostatic pressing, just for reference, that's something that's done pretty commonly to typical metal printed parts, like powder bed ones. It's a stress relieving process due to the fact that when you print with a laser, you induce a lot of internal stresses. We don't generally have to do that on our parts, mostly because the fact we're sintering all together at once. There's no added kind of introduced stresses inside the part. I hope that answered your question. If you want to clarify that, we can maybe try our best. But I don't know that acronym. That's interesting.
Yeah.
All right, so I think that's all that we've got for you all today. Thank you for tuning in, and it looks like our next AM Friday will be in 2 weeks.
Yep.
So we will see you then.
All right. Thanks for your time and happy printing.